Hello, good afternoon. Welcome to the second part of this Ice and Snow session. It's my pleasure to chair this session together with Lynn Rouillet. I'm Otmar Frey, and we have a lineup of five very interesting talks in front of us. Make sure you stay after the session as well for the roundtable discussion, as already announced in the previous session. Also, the chairs of the the previous Ice and Snow session will come in, and we'll do that together. So, without much further ado, I want to announce the first speaker. It's Jeff Stacey from Simon Fraser University, and he's talking on snow depth penetration experiment for ESA Harmony mission. Please.
Hello, everyone. I'm Jeff Stacey. I'm presenting on behalf of my co-authors, Usman Ahmed and Bernard Rabas. Usman was originally supposed to present this talk, but he couldn't make it, so I'm here instead. And I'll be talking about our snow depth penetration experiment for the ESA Harmony mission. So the objective of the study is the measurement of the elevation bias of C and X-band single-pass INSAR data acquired over glacial accumulation areas as a function of incidence angle and snow firn properties. We're doing this in order to improve models that correct this penetration bias in topographic products produced by the ESA Harmony mission. So we did this experiment using the SFU airborne radar FODAR system. So this is our comprises three radars. So we have an X-band, a C-band, and an L-band radar. Of interest for this talk are the X and C-band because they have an across-track interferometric baseline, and also the optical structure from motion, or FODAR system. This is oblique looking, so it's coincident with the SAR swath, so we can get surface DEMs from the optical system, and then X and C-band radar DEMs over the same area. Here are some system specifications for the SAR system. Again, what's mostly interesting here for this experiment is the X and the C-band systems. The X-band is a pulsed linear frequency modulated radar, whereas the C-band is LFM-CW. This doesn't make much of a difference in terms of the experiment, but they work considerably differently. One thing to note is that the X-band radar is significantly higher power. So it has 25 watts of transmit power plus an extra 50-watt amplifier. Whereas the C-band is only 1 watt of transmit power, so our signal-to-noise ratio is quite a bit lower. You can see some examples of other imagery. So that top image there is the L-band. It's a polarimetric image, and then on the bottom is a false color image of our 3 frequency bands over a forest scene. The FODAR system, which is the optical system, FODAR stands for Photo Detection and Ranging. This is a system that was developed by Fairbanks FODAR, and we use structure from motion photogrammetry to generate DEMs, orthomosaics, so like aerial photography all stitched together, and we've also been experimenting using this for motion refinement for our SAR focusing. This differs from conventional photogrammetry equipment in that we use an off-the-shelf DSLR camera coupled with our survey-grade IMU GPS system that's already integrated into the radar. So we're not using ground control points, we're just using our knowledge of the aircraft's position and orientation to do the processing for this. The area of study is in Kluane Lake National Park Reserve in northwestern Canada in the Yukon Territory. You can see where this is on the map on the left, and on the right is just an image that I took out the window of the aircraft. In the back there is Mount Logan, the tallest mountain in Canada. And this is the accumulation zone of one of the glaciers that we studied in this project. Some more detail on the area of study. So we fly out of an airstrip on the side of Kluane Lake, which is in the top left of the map here. And we fly into the ice fields and gather data at several different elevations on the glacier, because that's one of the parameters that we want to investigate in terms of penetration and its connection to elevation. Bottom right is the aircraft that we use. So for the experiment, we did simultaneous collection of X and C band across-track interferometric radar data with a FODAR acquisition at the same time to give us a reference surface. So the FODAR is taking pictures, so it's only getting the top surface. So that gives us a surface model, and then we compare that with the DEMs generated with the X and C band that should be below the surface somewhere. Then we do ground truth as well in order to measure snow properties so that we can correlate that with the penetration data that we've seen. As you can see on the right, this is a bistatic cross-track interferometric layout. So we have the transmit antenna in the middle and the two receive antennas with a total baseline of about 1.3 meters. As for our methodology, we deployed corner reflectors on the surface of the glacier for calibration and as a phase reference. So at the corner reflectors, all three of the DEMs should coincide because we're getting scattered from a corner reflector on the surface. So we should have the good agreement between the phase of the interferograms and the FODAR DEM at those points. We've also included exposed rock in the scenes because eventually we want to not have to deploy corner reflectors because that's a lot of work. We can't do that with the radar in the plane, so that involves separate trips out to deploy these. And it means that there's only certain areas that we can go because the plane has to be able to land. So by imaging exposed rock, we're hoping that we can use those as surface references instead of these separately deployed corner reflectors. We also dug snow pits for ground truthing to measure the snow properties. Then we did our X, C-band, and FODAR data collection all at the same time. The data was processed. We have several different processors that we've used to varying degrees of success. There's the Artemis Cicada one that was provided by the radar manufacturer, and then two in-house developed processors that have provided different levels of quality. And then we did some preliminary results and analysis. There are some, well, I'll present these later, and some of the drawbacks in our current analysis. So the workflow for the processing. It all kind of starts with the FODAR data collection. So we collect the FODAR, process it into a surface model or a DEM of the snow surface, and then use that to generate reference topographic phases for the X and C band interferograms. Then we process the X and C band data and flatten them using the reference surfaces generated from the FODAR data. Then using the phase, the flattened phase, we can convert this to a free space equivalent propagation depth or penetration using this formula at the bottom here. So you can see that it's free space, so this doesn't account for the snow properties at all, but it does account for some geometric effects of the penetration. So we've had quite a few field campaigns trying to gather this data and quite a few setbacks during this project. So our first attempt at gathering this data was in April 2022. We worked with a glaciologist also at Simon Fraser University named Dr. Gwen Flowers, and she collected wonderful ground truth data, but we had a hardware failure in the radar and weren't able to collect any C-band data. So we only have X-band data from then. We tried again after fixing the radar in August 2022 without ground truth for de-risking purposes. We were able to gather good C-band data, but we had lower SNR than we expected. So further investigation revealed antenna problems. We fixed those antenna problems, went back in April 2023 with the new antennas that could deliver 5 times more power onto the scene. And then the aircraft engine broke. So the turbochargers on the engine broke and we couldn't climb up high enough to get above the glaciers. So the weather also prevented landing, so no ground truth. We did get some data and some limited ground truth data from this campaign, but definitely not the full set that we wanted. We also had some range artifacts in that data, which we managed to quickly ameliorate and come back in May 2023, where we were able to get good C-band and X-band data over 2 of our sites. Also, coincidentally, there was a team from the University of Maine at the Eclipse Dome site, and so they were able to get us some very good quality ground truthing data. We returned just a few weeks ago in August 2023 in order to try and complete this project. But again, we were able to get 1 snow pit done, and then weather delayed our radar flights, and then we had a very scary in-flight engine failure that ended the campaign early. So again, we weren't able to gather great data from that campaign. I've got some examples here of those range artifacts that I was talking about. So this is the April 2023 data. You can see the C-band data. You can see these lines in constant range. And then in May, we were able to resolve these through messing with the radar parameters a little bit. So now I'll present some preliminary results. These are by no means a final analysis, but just an example of what we've done with this so far. So this is from the August 2022 campaign. You can see the various products that we're working with on the right-hand side here. So this is an orthomosaic, which is all of the FODAR images stitched together. So it's like an aerial photograph. Then the FODAR DEM that we generated over the glacier, and then an MLI from the C-band and X-band images. This is the interferometric programming, so you can see the MLI at the top again, the raw interferogram, and then the interferogram flattened using the FODAR DEM. The purpose of this slide is basically to show that our rock referencing method is working. So we're basically able to get very close to zero phase over the rock when flattened with the FODAR DEM. So that tells us that the rock and the FODAR DEM are very close to each other at both wavelengths. So we are getting surface scatter there. In April 2023, again, this is a summary of the data. You can see actually pretty well in the C-band MLI, we've got the exposed rock on the right-hand side, and then our two corner reflectors in the data as well. Kind of one's close to the middle and one's on the far left. Here's the interferograms from that campaign. So again, the raw interferogram and the flattened interferogram using the surface DEM. And here, based on the corner reflector data, we can look at the difference between the surface scatter and the X and C-band scatter. And we're getting, so at X-band, we're getting about 230 degrees of phase difference, which corresponds to about 7 meters of free space equivalent penetration. At C-band, it's even more, so 290 degrees of phase difference, which is about 18 meters of free space equivalent propagation. Now, again, this hasn't been converted into actual propagation into the snow, but still, it's what we've got so far. The May 2023 campaign, again, here's the same figure, basically. Now, the issue here is that it was very windy during this campaign. We had a lot of inclement weather trying to fly over the glaciers, and so we still haven't been able to fully work out the motion artifacts in the interferogram. So basically, when the aircraft rolls, your baseline changes, and so you get these extra fringes showing up. We're still working on correcting this for the May data, but hopefully we'll be able to do that soon and get some good results out of it. So as far as a conclusion, I'm not sure where I am for time, but despite multiple adversities in our data collection campaigns, we still have a good data repository for more detailed analysis. In order to achieve the ideal project goals, which is spring and fall acquisitions with concurrent ground truthing, we will have to do more acquisitions. That's just the way things go. The focusing quality of the original Artemis processor was very poor, which led to very low phase quality, but we've improved that significantly, such as the removal of those artifacts and just better phase quality in general. The rock method that we're trying to use seems to work as expected, so we're hoping to be able to replace the corner reflector calibration completely with the rock-based calibration. We were a bit worried at first about the small baseline, but it actually ended up being good because we have quite a bit of penetration. So the small baseline means that our ambiguities are very far apart. So we don't get too much wrapping as we get the penetration, which is nice. We're waiting for the University of Maine field campaign ground truth analysis, which should give us more insights about the snow properties during the May campaign. And yeah, hopefully that will improve our analysis a little bit. So overall, I think that we have promising research outcomes, and we are going to make, hopefully, a good contribution to the ESA Harmony mission objectives. Yeah, that's all I have. Thank you.
Thank you very much. We have plenty of time for questions, please. Yeah, over there.
What did you expect the penetration to be at those frequencies?
It depends really heavily on the snow properties. So depending on the amount of liquid water in it, or the moisture in the snow, it can vary wildly. Also, the density of the snow. The measurements that we've got here are about what I expected, but I'm not an expert on this kind of penetration measurement, so yeah.
Is that better? Yeah, cool. Yeah, thanks. I just wonder if you had any plans to do acquisitions in places where you might expect there to be features in the fern pack below the surface, like ice lenses or fern aquifers with this work?
Sorry, could you? I couldn't hear the first part of that.
Oh, sorry. I was wondering if you had any plans to do acquisitions where there may be features in the fern pack below surface, like ice lenses or aquifers.
Yeah, so the acquisitions over Eclipse Dome, so based on the early analysis of this University of Maine field data, there were significant ice lenses and like ice layers in the snow below there. So we should have some interesting data soon to look at with those features.
Other questions? I do have one regarding, it's more a technical curiosity. So you're using a time domain processing approach, but as I understood, you still process kind of in a standard SLC configuration, or you go to a geocoded product at the beginning. How does it work? My understanding was more like you do a classical processing and then do the flat earth removal or topography removal.
Yeah, so it kind of works differently for, we process these in a couple different ways. So some of these scenes were processed with a range Doppler processor, so they're happening in the range Doppler geometry anyway. And actually for the time domain processed ones, yeah, so we can focus them in a geocoded grid, and then but we need to process them together with the X-band, so we're actually resampling them back into the range Doppler geometry. Also, with the newer processor that I've been developing, you can just focus. It's a time domain processor, but you can just focus onto a range Doppler grid, and so that's what we've been doing more recently.
Okay, thanks. We still have time for one or two questions. Yeah?
With the corner reflector and the two frequencies, C and X band, you mentioned penetration, some numbers, penetration of 7 meter and 18 meter.
Yeah.
Derived from the phase. For me, it was really not clear how you come from phase to these numbers.
So it's basically the way that you would create a digital elevation model from a cross-track interferometry. That's what we're doing there. So converting the phase into a distance, vertical distance, essentially. And the reason that we have the corner reflectors is there we should have only surface scattering, so we can kind of, that's our reference, and then we can see the phase drop into the snow, or the scattering center drop into the snow around those points.
So you compare the phase around the corner versus the corner?
Yes, okay. Exactly. Yeah.
Time for a very last one. Yeah, Charles?
Yeah, so the question was about repeat pass interferometry. We've flown the same, so as you saw, we've done multiple campaigns, and we repeated the same tracks on all of those. Again, we're having issues with phase artifacts in single pass interferometry, so repeat pass is even harder to get rid of those artifacts. We haven't really looked at the repeat pass here, but this is a data set that we could examine there, so yes.
Okay, thank you very much again.
Thank you.
The next talk is given by my co-chair, Lynn Royer, and it is entitled Exploiting the Sentinel-1 Extra Wide Swath Mode Archive for INSAR Applications with the Terrestrial Cryosphere. Please.
Thank you very much. I'm presenting also on behalf of one of my colleagues, Jelte von Roosveen, couldn't attend today, unfortunately. So this talk, we will present some results that were a part of a project funded by ESA with the idea to showcase the potential of using extra wide swath mode for terrestrial application in the Arctic and in Antarctica. So first, of course, when focusing on terrestrial application, we all used to work with interferometric wide swath mode. So the first question is why do we think it was interesting to consider also EV data for this purpose? So EV, as you probably know, is designed mostly for maritime, oceanic sea ice applications. All imagery is available in GRD, some in SLC as well, but mostly in GRD, and it's unfortunately not released all over in SLC. And that's because the intended use was not in SAR, right? But at the same time, EV is very similar to IV, except for the lower resolution. But on another hand, as you can see on the figure on the right, EV has a much better spatial coverage. So typically one standard Sentinel-1 slice can cover almost the entire Svalbard. So this is an example over Svalbard, right? So the question is how it can be useful, right, for polar applications, but not underused currently. And so the question is also, is the resolution an issue? So of course it's worse than IV. EV is about 2 to 3 times worse in range and 2 times worse in azimuth, which give roughly 4 times worse in resolution. But at the large scale, if you see on the left, you cannot really see the difference. But of course, if you zoom on this yellow box, you can see the difference in terms of visibility of the crevasses. So with IV, you can really follow individual crevasses, while in EV mode, it's really fuzzy what you can actually see. And if you look at interferograms, densely spaced fringes cannot be resolved in EV, while it can in IV. So that's an open question. Can we basically use EV for this kind of application? And that was the goal of the project, to test several applications. So as it is, again, maritime and sea ice mode, EV mode is acquired extensively in the north and the south, as you can see on the top right image. And because the satellites have a polar orbit, there is a very short revisit time, up to daily for some regions, when 1B was still available. Again, so the point is that because of this amazing coverage, both in space and in time, can we use this data for application, cryospheric terrestrial application, for example, glaciology and permafrost applications. So to show you some kind of differences between IV and EV in terms of coverage, here are the first 2 examples over ice-free, or it's not fully ice-free, but typically for permafrost applications in Svalbard and Canadian Arctic. And for Svalbard, you can see that there is way more EV than IV, especially in the descending mode. So the ascending mode is lacking in EV, and that's because there is a conflict with sea ice use. Basically, well, yeah, this has to do with the acquisition time of the EV scene for sea ice services in Norway. And it's the same case for Canada. It's extremely well covered with EV, both in time and space. And this could also really be valuable for permafrost studies. If we think about now ice sheets or ice shelves, it's the same situation. Typically Greenland, we can see that it is really well covered by EV. And the main advantage here is to increase the sampling rate by combining IV and EV mode. And at the same time, EV and IV mode have different orbit geometries that could be combined in an interesting way for the ice sheet. While in Antarctica, it's IV is still the preferred mode for this kind of studies, obviously, but with EV we can double the volume of the data volume. And especially in East Antarctica, and where you have this black box, there are very, very few IV available, and it's lacking 6 days repeat. That is really valuable for grounding lights detection typically. So this FIS, this is a Finbull ice shelf that is shown in black orange. And you can see that there is very few data, and that's because it's located at the 0 meridian. So there is a gap in terms of IV observations. And this is where my colleague here, Jelte, decided to focus most of his work. And so here it's we're zooming into this region. And if we can see that it's on using IV, it's covered only by 12 days, 12-day stack, and one only. And so it has never been 6 days, so the grounding line basically had never been really well studied in this region. The last estimate was from the 90s using ERS. And when we look at EV mode, of course, you can see that it increased the data coverage, and you can go to 6 days also repeat pass. So basically, it enables higher sampling rate, combination of observation, and that's why Jelte also chose this area to go further. So now going to some results regarding the glaciological part first, and then some example for the permafrost application. So Finbull ice shelf, it's a large ice shelf in Queen Maud Land. The flow speed is up to 750 meters per year. And as I said, the last known grounding line is from ERS data, or like the INSAR-made grounding line is based on ERS data from 94. And so on the image on the left, on the bottom left, you can see an example of two interferograms that have been subtracted to double the difference procedure to obtain grounding lines. And what Jelte did, he basically processed all 340 scenes, created all 6 and 12-day pairs in a daisy chain procedure to create double differential interferograms and delineate and grounding lines. And so we will focus in the next slide on this orange box. That is where there is the fast-flowing part. It's a grounding zone with the fast-flowing part of Finbull. And in this area, it was more or less impossible to get good result with IV mode, as it is only 12 days repeat pass. So it's too fast, it decorates too much. So if we see now a bit closer, so we're at this grounding zone. So using one orbit, we can create combination of INSAR pairs. And here we show 2 years time series of these daisy-chained interferograms. And you can easily see on the animation on the left that stopped for some reason. Now it's starting again, good. You can see the variation in extent of the grounding and the flexure zones. And so based on this, then we can retrieve the maximum seaward extent, the maximum landward extent that is used then to define the grounding zone width, and also studies which give information how the ice shelf is migrating due to changing oceanic tides and atmospheric pressures. And and it's pretty large in this area, so it's 13 kilometers of grounding zone. And the extent of which the ice shelf is bending, which is the flexure zone, is also pretty large, so more than 34 kilometers. Now going to another application in another area, so we're going to Svalbard. And the point was to see if it was also possible to use EV for studying velocity variations on relatively small glaciers. So here 4 EV SWATs were used, descending modes, because ascending mode is not available again. We generated 6 to 12 days interferograms, and mostly in winter, because the coherence is dropping in the middle of the summer due to melt and rain. And the results show that it's actually quite fine to capture slow-moving ice, so we're speaking about slow-moving glaciers here, even on relatively small glaciers. And in the map in the middle, you can see the different points that were acquired with, so it's a GPS stake network from the Polar Institute, measuring how these glaciers are moving, and then we comparing the result of the EV velocity analysis along the central line, following a bit the same central line than this GPS stake network. So if we look at the results, you can see that, to go back a bit, it's actually a case of a glacial surge. So a glacial surge is when a glacier advances really rapidly and can go over 100 times more than the usual velocity of the normal velocity of the glacier. And this is something that is not really known. The process that is behind is not really known, and often you discover this when the surge has already started and it's somehow too late in terms of to use these kind of techniques. You have to go for offset tracking because it's really too fast. So the point with this result is that you can actually, on slow-moving glaciers with EV mode, because of the density of the data we have, actually track the change of movement of precursory, actually, to a surge. So on the graphs, you see on the left, both are showing velocities along this central line, but on the left you have the annual means, so showing this increase of velocity from 2018 to 2021. And on the right, you see individual observations. So, and the goal was also to look at differences between summer and winter period, or late summer, fall, winter. And so you can see that it's more quiet before summer, and then it's getting faster after summer, and this is because there is more water in the system, and it's lining basically faster. Yeah. So now, briefly, conclusion, how I'm doing with the time. I think it's probably okay, yeah. First part, conclusion for the glaciological part. So we can see that EV can basically generate time series of ice shelf grounding lines from different orbits. And the amount of data is really nice to have this information about the grounding zone variability. And at large scale, but also short-term variations. And in this area, it has not been possible before, basically. And what is the challenge now is comparing the previous information from ERS to what we got, so that's I think what YELTE is working on right now. And regarding Svalbard, so we could see that the data coverage is really helpful to understand the changes of velocity even on relatively small glaciers. And just a note that actually we use a quite small multi-looking factor to overcome the low resolution, and still it's relatively good coherence on many of these interferograms. So that was actually a surprisingly good coherence even on 12 days interferograms. And so the idea is now also to show that there are many potential applications. So we will not do everything in that project, but I think we can use EV for many other things like crack identification, capturing sub-glacial lake drainage, etc., etc. So I think that opens the door to many more things. So now I will move to some results for permafrost application. I will not be too long about it, but just to say also that this is more what I'm doing, permafrost studies. So we decided to perform our test in Svalbard, and this is because we have long experience using IV. So in Svalbard, the ground surface is really dynamic due to seasonal freeze and thaw processes, especially in the upper part of the ground that is seasonally thawing. And this results to ice melting and formations that actually subside the ground and heat the ground on a seasonal basis. And in addition, on the slopes, as you can see in this sketch, which is a kind of cross-section in a valley, you have also many different landforms creeping down the slopes, especially where there is high water ice content. So, 3 minutes? Yeah, I will manage for once. The question was why actually using EV, because we have, again, IV mode available, and we have worked with IV before. But as you can see, again, the coverage is really different, and we can actually have, there are 8 tracks, I believe, with EV, and we have 1 ascending and 1 descending with IV. So there is, of course, a question of temporal resolution, that we can theoretically increase the temporal resolution if we manage to merge in a good way this time series. And of course, you get also more views, so we can go from line of sight measurement to 2 to 3D displacements. And in the future, to upscale the investigation of ground movement in Svalbard, we can also process maybe in one go some things and have the entire archipelago covered. So that was the idea, to test a bit, and the first thing we wanted to check is that if we process separately IV and EV, can we get the same pattern, basically. And so here we focused on a flat lowland area, so the main area you see on the maps under is a valley bottom, where you expect it to have vertical seasonal subside and sieve patterns. And the dark red zones are where it's subsiding more because it's ice-rich in the ground. And so we process separately with the same SBAS processing chain, IV and EV, and you can see that there is a good general consistency in terms of spatial pattern, but not only spatial. If you look at time series, you can also see this seasonal cyclic effect, so subsiding during the summertime and heaving when the ground is refreezing. And last slide. So this is a bit ongoing work and next step. So the goal is to process and combine all these different time series to really increase the resolution to something that is daily. And on the left, you can see the list of tracks we have processed right now. So it's not fully comparable yet because it's not corrected for time reference and it's a single resolution difference and such. But that's where we want to go, basically. Yes, and so I think just the last final word is that I think EV is underused, basically. So there is a huge potential for terrestrial application.
Thank you very much. I think we can allow a quick question if there's one. Otherwise, you can. Yes. At the very top.
Yeah, thank you for a great presentation. So what recommendation would you give to ESA about the availability of EW SLCs? How did you get this thing for yourself?
It would be good to have SLC everywhere.
Right.
But typically, when you think about that, 1B is not available anymore, and it's often affecting permafrost areas where it's maybe not the priority, like outside Europe. This could be a way to overcome some of the data availability to actually, to provide the SLC data.
Yeah, do you have some fallback between everything all the time and some other requirement or recommendation, because everything will be a lot?
Yes, I can take that with my colleague Jelte and have a more, or we can discuss after for something a bit more concrete. But I think having the SLC available, is it not realistic for like the land area? Obviously, we're speaking about the land covered.
Yeah, I don't see Nuno Miranda in the room who would have the answer for you on the spot, but I think we can discuss this in the round table soon.
Yeah.
It's noted. So I think we have to move on. So I think you can announce the next talk. Thanks again.
Yes, of course. Me? Oh, I'm sorry. I got overwhelmed being both presenter and chair. That's not good. Sorry, the next presenter is Kristina Belinska and, from DLR, and she will present on repeat pass interferometric and polarimetric SAR data for snow water equivalent retrieval.
Okay,
Thank
thanks
you
for the introduction. And welcome to my presentation on using repeat pass interferometry and polarimetric SAR data for the retrieval of the snow water equivalent. And as a short introduction, the snow water equivalent describes the amount of liquid water which is contained within a snowpack. So it would be the depth of water if the snowpack melts instantaneously. And to calculate the SWE, it can be approximated by the product of the snow depth and density set in relation to the density of water. And the SWE is an important parameter for hydrological and climate models, for water resource planning, and especially when the snow starts to melt, it's needed to make flood predictions. And for repeat pass SAR interferometry, so to look at the same spot at a different time, a SWE retrieval model can be used, which relies on the fact that the radar waves are refracted in the snowpack. And here you can see an example. So in the left plot, you can see a radar wave traveling to the ground. And when the ground is covered by snow, the radar wave is refracted because snow has different dielectric properties than air. And then when comparing no snow to snow conditions, a difference in the optical path length can be observed. And this comparison not only works for snow compared to no snow condition, but also if there's already an existing snow cover and the SWE is increasing or decreasing between the measurements. And here it has to be pointed out that we have to look at dry snow so that the radar wave is able to penetrate through the snowpack. And when now considering the geometry of the scene, the path delay can be translated into an interferometric phase. And it depends on the wave number, on the snow depth change, on the incidence angle, and on the dielectric constant. And we're now using an empirical relationship for the dielectric constant. The SWE change independence of the interferometric phase can be calculated. And you can see that there's a linear relationship, and the SWE changes, in the plot you can see the results for X, C, and L band, and you can see that the SWE changes for L band are higher than for X band. However, this method has some limitations because we're looking at repeat pass SAR measurements. We have temporary correlation between the acquisitions, and also phase calibration is needed. Moreover, as will be seen later, the phase delay depends on the polarization, which needs to be taken into account. And as the interferometric phase lies in an interval between -pi and pi, only a limited range of SWE values can be retrieved unambiguously, and outside this interval, phase wrapping occurs. So when the phase will get larger than pi on the very right side, it wraps, and therefore the SWE values will be underestimated. And this can be corrected by adding the missing phase cycles. So the goal is to calculate the sweep change using the interface and then to correct the phase reps due to large sweep changes, and in order to then obtain a final sweep estimate. And there are different ways to do so, and the first possibility would be to use in situ measurements to correct the missing phase cycles. So over a test site of Svalbard, using TandemX data, the range where the sweep change can be retrieved was very small. It was between minus and plus 8 millimeters, and you would have underestimations of the sweep changes above this threshold. And here you can see an example for the part of the time series. So you can see on the y-axis the sweep change, and on the x-axis the dates, with always 11 days temporal baselines because we use TandemX data. And in red you can see the ground measured sweep changes, and in blue you can see the retrieved INSA sweep changes. And there are 2 points where there are no the INSA sweep estimates, and it was where the coherence was below 0.3, so these values were masked out. And yeah, you can clearly see an underestimations. And now the in situ measurements are used whether the actual sweep change was above this threshold, and if yes, the missing phase cycles are adding, and following results are obtained. Like here, it has to be pointed out that because we're looking at X-band, this phase rep correction has a high impact on the results, but it just to show that for 11 days in X-band, the phase reps are one of the main limitations. And another possibility to correct the phase rep would be to use multi-frequency sweep estimations, because we want to do the phase rep correction without the need of additional in situ measurements. And here the basic idea is to use the sweep change from a longer wavelength, like for example L-band, because of the high phase rep threshold, to correct the sweep change estimates from shorter wavelengths measurements, like for example C-band. And the basic idea is like to calculate the sweep change, including the standard deviation from L-band measurements. And when they're below the phase rep threshold for the C-band measurement, no correction is performed. And if they're higher, then the missing phase cycles are added. And here's an example for Sentinel-1 data over a test site in Finland. And here in the plot, you can see again the sweep change and the dates. And here we have always 6 days temporal baselines. And in orange, you can see the ground measurements. And in blue, you can see the retrieved sweep values. And now LS2 data from the same winter is used to add the missing phase cycles. And we obtain following results. So now we have some overestimations, but the accuracy increased compared to no correction. But here it has to be pointed out that the winter was not optimal because the temperatures were often above 0 degrees, and therefore there might be some melting in the snowpack, and the radar wave was not able to penetrate to the ground. But however, this multi-frequency correction might be important for upcoming multi-frequency SAR missions. And the third correction would be to use parametric measurements, because there's additional information on the snow accumulation contained in the copolar phase difference between the VV and the HH channel. And because snow has an anisotropic structure, the signal delay, and therefore the propagation speed depends on the polarization. So in the plot you can see on the left side, when the snow is settling, it forms the beginning more horizontal structures because it's compressed due to its own weight, which can be associated with a slower propagation for the horizontal polarized radar wave, which can then be associated with positive CPD values. And after some time, the snow forms more vertical structures because of temperature gradients, which can be associated with negative CPD values. And therefore, the CPD can help to detect snowfall events. And a model has been proposed where the snow is modeled as ellipsoidal ice inclusions in air. And then when assuming anisotropy, so the snow structure, and the density of the snowpack, the dielectric constants, and also then the refractive indices for the HH and VV polarization can be calculated. And in the end, we obtain a function for the CPD, which depends on the wavelength and the incidence angle, the snow depth, the density, and the anisotropy. And then when assuming density and anisotropy, the measured CPD can be used to invert for the snow depth. So here again, the example for the TandemX data over Svalbard. And we're now calculating the sweep change between the measurements and use that to calculate the snow depth change. It is checked whether the sweep measurements are above the threshold, and then the phase cycles are corrected according to that. So here, not all phase cycles have been corrected properly, but most of them. So the advantage to use the CPD is that it's less sensitive to phase reps, and also that no absolute phase calibration is needed. However, there's a limitation both for INSAR and POSAR. So between 2 measurements, because we're looking at repeat pass, the sweep can increase or decrease, or the microstructure, so the anisotropy can change. However, a phase change is obtained for both. So we will obtain also the INSAR phase, even though the sweep stay constant and just the anisotropy changes. And the question is whether it's possible to separate these effects. And for that, the idea is to combine the de-Insar and parametric measurements in a Pol-Insar approach. And for that, we want to calculate the temporal coherence regions. So we need 2 parametric acquisitions at 2 different times. And we use dual pol data. And from that, we calculated the coherency matrix for image 1 and image 2, and also the temporal Pol-Insar matrix between them. And this is then used to calculate the temporal parametric coherence, which can be seen in the equation below. And here omega are the unitary vectors of the different polarization states, and for now we always used omega 1 equals omega 2. So here's an example for the data. So this is from the tandem X data over Svalbard for an event where we had a rather high snow depth change, a high speed change. And here the coherence region is plotted in the unit circle. So the radial extent ranging from 0 to 1 is the coherence, and the phase is the phase. And here in this coherence regions, we plotted 500 random polarization states, so 500 random omega vectors. And because we used Pauli basis, the alpha angle, which can be plotted too, which ranges from 0 to 90 degrees, with 0 corresponding more to surface-like scattering and 90 degrees to dihedral. And you can see that smaller alphas are more located at the higher parts of coherence region. So now the question is which snow parameters are influencing the location and the extent of the coherence region. And for that, we try to model that. And we want to model a surface which is covered by snow. And for that, we need a scattering matrix. And we use the scattering matrix of a corner reflector for simplicity. And to model the influence of the snow, which is the refraction of the radar wave, changing the propagation, we included the propagation matrix. And inside the propagation matrix, we took this optical path delay from the INSAR model and the electric constants from the CPD model. And now it's investigated how different snow depth and anisotropy changes will influence the coherence region. So here you can see an example for X-band. For the first case is a SV increase. So the anisotropy and density are set to constant value. And the snow depth at the first acquisition is set to 1 centimeters. And then it's increased by 4 and by 7 centimeters. And here you can see now again the polar plots of the coherence region for 500 random polarization states. And as we have not included any decorrelation effects now, the coherence is at 1. And you can see that with increased snow depth change, the phase is increasing of the coherence region as expected. And the second snow change would be an anisotropy change. So now the snow depth and density are set to constant value, and initial anisotropy is set to 0.1 and then increased. And here in the plot you can see now less an effect on the absolute phase, but more an effect on the extent of the coherence region. And to look more into detail, so here's again the first case of the SV increase. And here the interferometric phase is plotted for the VV channel in blue and for the HH channel in orange. And yeah, you can see that the phase starts to increase with increasing snow depth change, but you can also then observe the phase drop between 4 and 6. And also increasing difference between the VV and HH channel can be observed, which can be also seen more in detail with the parametric phase. So in blue and green, you can see the CPD change, so which is the difference between the VV and HH channel, which is increasing. And in red, you can see the phase extent, so the width of the coherence region. And you can see that the phase extent has higher values than the CPD and therefore higher sensitivity. The second case is the anisotropy change. So here you can see also that the phase is increasing with increasing anisotropy change, but here the values are much smaller than in the SV change. And for the parametric phase, you can see the same behavior as similar, so also an increasing CPD change with higher phase extent values. So here the behavior is like really similar to the snow depth change case, and therefore it's not yet possible to separate these effects. And by looking now again at the real data, so here's again the example for the tandem X. And by using now the snow depth and SV changes, and assuming an anisotropy of 0.1, the model would produce the following coherence region. And to make it more realistic, we wanted to include decorrelation effects. And the first is the temporal decorrelation, which results from a non-uniform snow accumulation in the resolution cell. And here it's a constant shift of 0.75. And the second decorrelation effect is the SNR decorrelation. And here, by assuming a noise of minus 10 dB, we would obtain following coherence region. So this is now just a preliminary comparison, so it's not about the phase, but it's rather to show that the model is able to reproduce some structures which can be also seen in the real data. So just to sum it up, it was possible to use multi-frequency and parametric measurements to correct the phase reps. And by modeling the coherence region, the phase extent showed a higher sensitivity than the CPD values. And furthermore, the modeling of the coherence regions for different snow depth and anisotropy changes showed similar behavior as the real data. And yeah, for the next step, because it was not yet possible to separate the anisotropy and snow depth change, and therefore the aim is to further investigate the influence of different snow changes on the different polarization states. And the goal would be to establish a retrieval based on the coherence region parameters. Yeah, thanks.
Thank you. We have a lot of time for questions.
Thanks, very interesting presentation. Could you explain why the phase extent of the Pol-INSAR is higher than the sensitivity of the CPD? The CPD shows very small phase changes, but the phase extent showed much higher values. So it's more sensitive. That's a conclusion from this graph on the right-hand side. Could you explain why this is the case?
Yeah, I think like when we're looking at the CPD, we are looking just at the HH and VV polarization, and like from this coherence region, we are like taking different combination of HH plus VV and HH minus VV, and apparently there are like some kind of combination of these Pauli parameters which have a higher phase diversity than just looking at the CPD.
Brings me to my follow-up question. How do you distinguish between a CPD of 180 degree between VV and HH and double bonds, which is 180 degree?
Yeah, that's a good point. Yeah, I haven't checked it yet.
That's the reason why I didn't look into Pol-INSAR, because double bonds looks like a CPD of 180 degree, and it's completely different effects. I couldn't solve that, maybe you can. Thanks.
Any other questions? If not, I think we continue.
Okay,
Thank you so much. The next presentation is from Fabio Bavanga about rock glacier activity by exploiting multi-band SAR data through differential SAR interferometry and offset tracking.
Okay, thank you. So this work has been carried out in the framework of Cryosar project funded by Italian space agencies, and my co-authors are from National Research Council of Italy Iria Institute, from EURAC Research, and from Geophysical Application Processing. So this is the outline of my presentation. First, I will briefly introduce the problem, then I will present some result coming from multitemporal interferometric SAR for deriving displacement. Then classification of rock glacier activity according to these results. Then we focus on a specific rock glacier, Lazaun test case, where we also performed intensity tracking, and then some results analysis and final comments. So rock glacier are basically a mix of ice and rock, and they represent an important water source, particularly in this period of climate change, and so in areas in drought-prone regions. And basically, the flow depends on the water content on the layers underground, and the temperature is considered one of the main factors triggering this and controlling this displacement. And so it is quite important to monitor and measure the displacement along time, so the evolution of kinematics, and try to correlate with the temperature variation, especially in relation to the temperature rise in ongoing. And of course, one of the tools that can be used is differential cell interferometry. However, the application, which is very effective for measuring ground instability, but its application in this context, so for rock glacier in particular, is quite demanding and poses several critical issues, basically related to the steep topography, which of course induce some layover and shadowing effects. The signal decorrelation because of the changeable snow cover conditions, and of course related to the kinematics, because we have in particular very strong, very high displacement rates, which leads to aliasing, phase aliasing. And here you can see the test site. We focus our investigation on the Italian Alps in Valsenales, where there are a lot of these rock glaciers. And we acquired a quite large data set made of 345 Sentinel-1 acquisitions. And then we focus in particular on one of the rock glacier in the area of interest, the Lazaun rock glacier, because it has been already investigated in the past by using several technologies, including ZNSS, inclinometers, and also ground-based differential cell interferometry. And just, so we started by, because of, we are very well aware about the critical decorrelation ongoing in this kind of area, we started by investigating the behavior of coherence a long time, and then we built up a stack of coherence by coupling consecutive acquisition in order to, let's say, decrease as much as possible the decorrelation, temporal decorrelation. And then we compute the average, in this case, in this plot, around the Lazaun test area, and we plot the average of the coherence. And you can see that, of course, a long time coherence is mostly quite low, except within this interval between this, among these red and blue vertical lines, which basically includes snow-free acquisitions. And what happened is that I plot a couple of images, which is typical images where one in case of high coherence, where in this case we can, in summer acquisition, when it is possible to catch clearly the signal related, the phase signal related to the rock glacier activity, while in case of low coherence, of course, the differential phase is practically unmeaningful. And so we have to deal with this, of course, very complex setting. And then we, after this preliminary investigation, we perform a multi-temporal differential interferometric processing by using the Spinua algorithm, which exploit both persistent scatter and distributed scatterers. And we get these first results. Here you can see the map of mean displacement rate computed of the selected coherent targets in the area of interest. And on the same image as have been also, you can see also the polygons corresponding to the rock glacier in the area as derived from a regional inventory map. And the color of the borders depends on the activity of the glacier. So we have active, relict, and undefined. And so, of course, the coherence target sometimes is lacking, and this is very. It occurs also in correspondence of several rock glaciers. So we try to improve these results by adopting some ad hoc strategy in the processing. And first of all, we eliminate the image, and so the interferogram where we have snow cover, according to our preliminary coherence investigation of the coherence evolution in time. And moreover, we try to at least partially overcome the problem of aliasing, phase aliasing, by forcing the algorithm to search for higher velocity. And basically what we did is to use iteratively the velocity estimator not centered on zero velocity, but moving to higher velocity values. And then we get these more interesting results. So of course the number of target increases, and the density is quite good to cover mostly all the rock glacier in the area of interest. And we see also that there are some rock glacier classified as, for instance, this one, the black one, classified as relict, where there are target showing deformation. So this means that these results demands for further improvement of the classifications. And so this is what we try to do. And so we try to implement and classification procedures based on these results from the SAR interferometry. And first of all, we compute the percentage of rock glacial surface covered by the coherent target, because of course the reliability of the information that we are able to use to classify according to the velocity each rock glaciers depends on the number of targets within the rock glacier polygons. So we build this automatic procedure, quite simple, to derive the density of the reliability of the information that we are able to derive from the multitemporal sun interferometric products. Moreover, we try to investigate also the spatial patterns of the deformation, and we, through also a K-means algorithm, we classify the velocities, and we see that indeed exist several classes. The velocities are quite well classified, and we see also that the velocity classes provide interesting results, because we see that often the velocity values increases coming from the border of the rock glacier coming into the inner part, because there we expect the higher value of deformation indeed. And so we try to use all these results, so the mean velocity, the cluster of velocity, as well as the density of target within the rock glacier borders, to derive a more reliable classification procedure. And this is what we get. This is a sketch of the flowchart. And basically we use this is based on the interferometric products, but we use also other inputs, so optical orthophotos, permafrost probability index, NDVI, for selecting area covered by vegetation, and also not only products from multitemporal sun interferometry, but also product coming from the standard interferometric product that we derived by coupling consecutive images. So just coherence map and differential phase maps. And these products are, this investigation is required when we have, in particular, when we have lacks of a coherent target. I will not spend more detail on the procedure, but you can see that there are some decision blocks which are based on the density of the and on the density of the target within the polygon. And so indeed, we have cases in which these ancillary data are very useful when, of course, we have lacking of coherent targets just where we need where we need, and this is basically due to the high velocity ongoing in the inner part of the rock glacier that we were not able to overcome by using the ad hoc strategies in performing velocity estimation. But in this case, we can use reliably the coherence. So you can see the black pixel here, which correspond to area where we have abrupt variation of the deformation, as well as, of course, the standard interferometric phase. And okay, then we derive a new classification map. On the left, we have the original one. On the right, the polygon classified according to the refined procedure based on the interferometric results. And you see that there are several polygons that changed colors because they have been classified in different way. And in particular, we have example of like this one of rock glacier that has been moved from a relic class to a active class. And here, this is quite interesting one because again, we have a lack of coherence target within the polygon, but we use the information coming from the coherence and the standard DINSAR phase, as well as, of course, also the permafrost index and the NDVI. And this is the Lazaun test case that I presented previously. And also in this case, we have we experiment a lack of coherence targets because of the high velocity rate within the border of the rock glacier. And also in this case, of course, we see also that by exploring it's very interesting to look at the classes of velocity here. And so we can see that there are 3 classes of velocity, and the velocity increase in value while coming from the border into the inner part. So this means that the lacking of coherence target basically is related to the aliasing occurring in the phase that has not been recovered by the estimation procedure. And again, in this case, we reliably were able to recover information by exploring both the coherence and standard DINSAR phase. Like you can see here a couple of examples, as well as the optical orthophoto images. And in this case, we try to explore also the amplitude of the synthetic aperture radar, and we perform offset tracking by exploring, in this case, high resolution X-band data, because we need the techniques in this case needs high resolution. And we prefer to use intensity tracking because of the lacking of coherence, and so the speckle tracking is not reliable. So we use a pretty standard processing chain that you can see on the right hand of the slides. And we use TerraSRX spotlight images, Cosmos Skymed second generation spotlight images, as well as Cosmos Skymed street map images. The acquisition mode depends just on the availability of the data in the area of interest. And these are some results. The maps represent the deformation projected along the slope for the Lazaun rock glacier, and has been derived by processing pairs spanning 1 month, 1 year, and 2 years of. And here you can see that we can see that in all cases we see the large deformation occurring in the upper eastern part of the glacier, which is the area experimenting lacking of coherent target indeed. And we also were able to perform some comparison validation by using GPS data were available with the root mean square between 0.3 0.4 meters. And then we try to combine both results coming from the amplitude analysis and those from multitemporal sun interferometric processing. And here you see the maps obtained by superimposing the coherent targets mean rate velocity over the four displacement map derived by Cosmos SkyMed processing. And again, we can clearly see that where we have the larger deformation, we see lacking of coherent targets. And so the two techniques are quite complementary. And so it's quite interesting to combine these to derive. Yes, this is almost my last slides. So then we try to, of course, correlate these results, this deformation with the temperature air water content, because as I introduced, this is the main factor influencing the velocity and the flows of these rock glaciers. And we see that basically concerning the intensity tracking, the summer temperature appear to produce larger shift due to the thawing rate of permafrost, while during winter the temperature does not seem to influence the movement, basically because of the snow insulate the rock glacier. And concerning the cumulative precipitation during winter, it can produce a higher displacement due to the heavier weight of the snow, and also due to the snow melt occurring in the late season, winter season. While in this case, summer precipitation do not show any correlation with displacement. So I conclude my presentation. This is just a summary of what I have already said during my presentation, but just to say, I would like to stress the fact that of course, we need to, in order to derive useful displacements information, we need to provide an ad hoc processing strategy for differential interferometry. And according to this interesting result, we derive an improved classification of the rock glacier. And okay, the intensity technique provides results complementary to the multitemporal sun interferometric products. Because it allows to provide displacement estimation of areas and periods not covered by the sun interferometry. And so you can see here some future works that we plan to do. First, we try to introducing automatic procedure for spatial and temporal analysis of the displacement map. We plan to develop the more reliable and automatic tool for integrating multitemporal sun interferometric product and intensity tracking product. And finally, we also will try to refine the classification procedure by introducing both intensity tracking result as well as result coming from L-band DIMSAR. Okay, that's all.
Thank you. We have time for one question or maybe two short ones. I may have one then. So which maximal temporal baseline did you use in the multi-temporal INSAR processing?
Yeah, okay. The procedure explored both permanent scatter and displacement scatter. So basically, we use a standard one single master processing. But of course, when we explore the distributed scatterer, we combine properly the acquisition according to the best coherence on the specific area. So it's depend on the contrary, when we use the single pairs that I showed, and so the single displacement map, we just look at the shortened temporal baseline instead of just one. So we couple consecutive acquisition. So basically 6 or 12 days because of the Sentinel-1 repeat times.
But because for now you have not really used the time series, you use more the mean velocity information for the categorization of active transitional relic, right?
Yeah, we did.
So you may have a better coverage if you use only 1 year without interannual.
So the one, yes, of course. This is one another. Yes, of course. We explore all the baseline by removing. Yes, I didn't say, but we removed the snow, the image with snow coverage, and then we use basically just the whole period covered by the acquisition. But we plan also to, of course, processing year by year in order to see also not only interannual displacement, but also seasonal one. Because at the moment, what we get is basically a rate which is an average of the yearly movement, okay, along the whole period. Not.
Yeah, no, interesting. Then I guess I used the entire time with my question, but if there is somebody else who is, we can continue to chat after.
Okay.
Yeah, so we move on. Thank you so much again. We move on to the last presentation from Thomas Nagler about experimental studies on dual frequency INSA application for snow mass monitoring.
Thank you, Lynn, for this introduction. In my presentation, I will present a field campaign that was carried out 2 years ago on the preparation of new future missions, and it is on the dual frequency INSA application for monitoring snow mass. The objective for this was that we are testing and evaluating methods for snow mass in alpine environment where high resolution of in the order of a couple of tens of meters to 100 meters is needed. And we are focusing here on repeat path interferometry, applying this approach. And this experiment was carried out with an airborne campaign in collaboration with DLR. And we want to prove a concept for applying a geostationary SAR system for INSA retrieval. It was an Earth Explorer proposal where we are having a C-band geostationary SAR providing every few hours an image of certain regions in the world, or in the Alps, for example. And this mission was not selected, but it is proposed to go on. And this campaign actually was evaluating the capabilities of such a SAR mission. On the other hand, we are also looking for upcoming missions like Roselle, polar orbiting SAR missions, and in support of preparations for these missions, we have carried out a couple of experiments, and in this presentation, I'm primarily reporting on the preparations for these polar orbiting missions. The test area was a high alpine region close to Innsbruck. It was at about 2,000 meter elevation in the lower part, reaching up to about 2,400 meters in the upper part. It was actually separate can be divided into 3 different regions, one at about 2,000 to 2,100 meters, which is called Unterer Boden. Then about 200 meters higher, the Mittlere Boden, and then the highest region, the Obere Boden, at about 2,400 meters. They are more or less flat terrain without forests or whatever, but of course there is this high alpine tundra regions, but we have also some boulders and rocky terrain on the background. For actually, you see here a SAR image which was acquired from the right side of the image, track 10. We are actually flying in ascending and descending mode from the south to the north and back forward, imaging the test area from both sides, which makes us, of course, also the opportunity to investigate the consistency between the different incidence or imaging directions and incidence angles on the different sites. This is one image geocoded, and you see here the regions, more or less what we are using then later on for analyzing the backscatter contribution, but also the phase, of course. They are homogeneous regions and flat terrain, and are really selected based on the digital elevation model, and also using the surface vegetation parts. We set up a couple of corner reflectors in the test area. They are used looking towards the ascending and descending track, so always one pair on each stage, and we had them actually oriented towards both sides, and we need this as a kind of reference for the reference of the phase. And at every overflight, these corner reflectors were cleaned out of the snow and were also remeasured in order to guarantee the elevation angle and the orientation of this part. For measuring, we as a radar device, we had the DLR FSAR system, which was operating at C and L band. So C band was at 5.3 gigahertz, and with a relatively wide signal bandwidth of 384 megahertz. So we had a very good resolution in the sub-meter scale. And for the L band, it was 1.3 gigahertz with a smaller bandwidth of 150 megahertz. Also with a spatial resolution of 60 centimeters up to 1.3 meters in azimuth and range. This is one example of the track 11 looking to the test area. You clearly see here the lower regions. There is some small bushes there, but most parts are actually this high alpine tundra. Then with MB is the Mittlere Boden, which is actually 200 meters higher above a steeper region. And the highest one is called Obere Boden. The corner reflectors for referencing are actually aligned on this line here. Now we had overall, we had 8 flights which were lasting for a couple of hours. So at each flight, we had about 20 acquisitions in the ascending and descending mode. The baseline was always kept very close to zero, so as good as it was possible. And on the beginning of March, actually, we were setting up the corner reflectors. And the flight 1 and flight 2, they were, of course, they had already some snow there of 1 meter, but there was no snowfall. And the last flight actually happened on the 19th of March, about 3 weeks later. And during this period, we were quite lucky because we had always very cold temperatures, as you see here on the temperature records. And when we are looking to the snow accumulations, we had 2 snowfall events, which is where we were also quite lucky. The first snowfall event was in the beginning of March with flight 4 and 6, snowfall event 1, which we called SE1. And the second, this was quite a small snowfall event actually. And when we are looking to the accumulation of the snow in all the 3 different regions, what I explained before, we had about 10 to 12 centimeters fresh snow accumulated. So this was very homogeneous. And the second snowfall event was a longer period, lasting actually from the 9th to the 19th of March. And here we had snow accumulations which was much higher, about 50 centimeters in the highest region and only 30 centimeters in the lower part. And through all these acquisitions, actually, we had dry snow conditions before and also after the snowfall. Just at the very southern oriented slopes, we had at the later, or at noon or a little bit later in the afternoon, we had a little bit of surface melt. And, but this was refrozen overnight, of course. And this surface melt did not disturb any of the measurements because most of the acquisitions were taken then actually in the early morning. Now we applied here the speed retrieval, so this method is quite well known. We are measuring the interferometric phase between repeat pass acquisitions from one track or the other, from both sides. We are observing the interferometric phase, which can be separated into a flat and topographic phase. Then very important is the atmospheric variability. For airborne conditions, this is not so critical because the path through the atmosphere is quite short, and in this case we neglected it. And finally, removing all the topographic contributions, we get a kind of phase contribution due to snow accumulations, and this can be formulated within this relation shown in this figure. And finally, we can simplify this to get a direct, very nice relation between the change of the snow or water equivalent, the snow mass, and the observed interferometric snow phase after removal of all the other contributions. And this depends on the incidence angle of the local slope and, of course, also on the wavelength. Just what I want to point out is the high sensitivity of this, and for L-band and C-band, both frequencies what we are measuring. And here on the right graph, you see the change of the snow water equivalent for one full phase cycle, independence of the local incidence angle for C and L-band. And when we look here, I give you here some numbers. For an incidence angle typically for 40 degrees, which was in the center of the image, we have at C-band about 29 millimeter of delta of snow water equivalent change, which corresponds for fresh snow actually only for about 20 centimeters. So this 20 centimeters snowfall in the Alps is a very small snowfall, can be also accumulated by snow drift. At L-band at 40 degrees, this is of course less sensitive, and one phase cycle is about 80 to 90 centimeters of a fresh snowfall, which is more typical. And this is, of course, therefore the L-band, beside all the coherence and signal stability, is more preferred actually than the C-band because we are relying for a typical snowfall in the Alps within one phase cycle. There are other issues what are critical issues for this. One is, of course, the temporal decorrelation. We know already that when we have snowfall or significant snowfall, depending on the frequency, we have a decorrelation and we are not getting out any fringes. Then what we need in order to calculate the snow water equivalent, we need at one point a kind of reference point. And this is in the area not so easy to select when you don't have any stable targets there, where you know that there was no snow accumulation, or a place where you know how much snow was accumulated. So this is also needed. It is a kind of critical when we go later on to the applications. Then the 2-pi phase ambiguity might be a problem. And what we also think for a larger scale, when we look for satellites, the atmospheric correction is a critical issue, because especially at C-band, when we're looking to small changes in the phase, the atmosphere in mountain terrain can have an impact. Now I show here the coherence and phase images at C-band. This is still in SAR geometry. All the analysis what I show here was done in single loop complex geometry. We see here the coherence at, for the snow event 1, which is the small snowfall up to about 10 centimeters. You see in the red, the 3 different areas at the 3 different elevations, but in this part we have more or less the same snow accumulation. We have the associated phase next to it, so we are within, easily within one phase cycle. And when we are going then, as a second example, to the bigger snowfall at the end of March, then we see that the C-band completely decorrelates, and the phase is in principle not useful. So when we are looking to the L-band, at L-band we see immediately, just comparing the same with the slide before, coherence for the snowfall 1, but also for snowfall 2 event is much higher. So L-band really is very useful, and also the phase gives us very nice information, and we can use L-band also in order to analyze the bigger parts. And now some results for these 3 different areas which are grouped together, and we did the analysis when we are averaging all the pixels within these regions what we have shown. On the first part, you see the L-band INSAR retrieval for the snow event for the 3 different regions, Oberer, Mittlerer, and Unterer Boden. So this is the small snowfall event. The gray bar actually gives you the average of all the measurements what we had done in the field during the overpasses. And we see that there is a quite good agreement between the observations and the the INSA retrieved snow water equivalent changes. But there are still some problems between when we are comparing, or differences when we are comparing track one, so one emerging geometry versus the other one. So this is the blue one versus the yellow one. We see that there are differences, and the main issue what we think is in the selection of the reference points. So the corner reflectors were quite tricky, and this one. What we also see in these figures is that there is no difference between VV and HH, what is also shown here in the two different colors, light blue and dark blue, or light yellow and orange. At L-band, so when we compare C-band retrieval for the snowfall event 1, we see also that the agreement is quite well, and we get the same values as with the L-band. We did not calculate actually the L-band, the C-band for the snow extent 2, because it did not work out, the phase did not correlate. And when we are comparing this example here for the snowfall extent 2, we see that all the measurements are agreeing quite well with the INSA retrievals. So we have here, I wrote here the numbers of the differences at snowfall extent 2, for example, the difference between the retrieved snow water equivalent change versus the observed one is about 1.6 millimeters. For the snowfall extent 1, is also in about 1.2 or 0.2 millimeters at L and C band. So quite a good agreement. So this shows is actually quite promising. We understand the physics of this method. We get good results when we are looking for a small scale. And the next question is, of course, how does this look like when we go into a map? We calculated now using the Trackit 10 as an example here, C-band on this side here for this small snowfall at the beginning, and you see that there is almost no variability in the snowfall, and this agrees very well to the observations. And just be careful here, the scaling is between 0 and 20 millimeters on this side. On the other side, we have here the L-band VV INSA data retrieval for the snowfall 2, for the bigger snowfall, but the scale is slightly different. It's 40 to 80 millimeters. And here we have, of course, some variability. In the deeper slope, the snow was moving down a little bit. So we see some variability in this one, which is also in agreement actually with the snowpack measurements, what we did during the observations. Now, how does this look like when we are going with these concepts toward a kind of satellite geometry? And I show you here one example for Sentinel-1 C-band interface, covering the very west of Austria, Engadin, and the eastern part of Switzerland. So Samedan is actually here one. So this is the Engadin Valley. I show you here the phase image. And two examples of the time series. We see here actually the first image was acquired for a 6 days repeat in November with a very big snowfall. Temperature was actually very low, and this is this example here. It fully decorrelates. So in principle, we have here about 60, half a meter of snow at Samedan accumulated. And actually, at the higher elevations where in the mountains, there was no signal correlation available. We could not find it out. In the Rhine Valley, in the upper part, actually, it was raining at this day, so there was no snow accumulation. And there we have, of course, coherence. The second example, what I show here, is one example at the end of January to 6th of February 2020 with a moderate snowfall at Samedan. And this is actually the red box here. We see here there was about, within this period, about 7 millimeters of precipitation. But the precipitation was here also actually falling here partly as rain, because temperatures are far above zero. And we have also snow melt in this part. And we think that due to this snow melt, although temperature at the second image was dropping, there might be still some wetness within the snowpack available. And this causes that we have actually almost no correlation within the valley. When we are going to the north, where the precipitation was actually increasing, we see again that there was no, the phase is actually destroyed. We have no single coherence available anymore. In the Rhine Valley, actually, we have no snow accumulation available. Again, rain, and the coherence is here. When we go to the south, this seems quite promising, but there was no accumulation of snow, so there was no snowfall. So we had a gradient of snowfall south of the Alps with the main precipitation at the main ridges, and north of it there was also no snowfall. How does the Alpband look for the second example from almost the same periods? This is the Alus Balsar image. We see one big example here going from Lago di Como towards the north to the Rhine Valley. So this is this area of interest where we did our field measurements. There was actually no snow accumulation in the south. Coherence is excellent. When we go towards the snow accumulation, it gradually decreases actually the coherence. And this is, of course, also even at Alpine sometimes really challenging. And unfortunately, where we had actually these field campaigns parallel to the Alus Balsa acquisition, so this is a 2 weeks interval, also quite a long interval, we were able actually to generate a kind of SWE-map for this period. So this coherence was actually above approximately 0.2. We were masking out layover regions and heavily dense forested regions. They are actually in dense forest, this is a kind of problem because there the phase is stable, but we don't get the signal from the snow. So we get the branches, the backscatter from the branches, the phase is there. This can be also helping us in order to bridge the different regions where we have actually open land with some snow accumulation. And when we are into comparing this with a couple of stations and field measurements, you see that we are more or less reflecting this snow accumulation, but of course more work has to be done in this. I have also to say that for the Alpine we did not correct here for the atmosphere. That's the last slide. So the Vergedal campaign-based L and C-band airborne SAR data confirms the high potential of the repeat pass INSAR approach for observing the mass of snow accumulating in alpine terrain. The FSAR data at L-band show high coherence and very good performance on the speech retrieval. That's very promising. Also, when we have higher snow accumulation. At C-band, we get good results when there is moderate snowfall. But for a dense snowfall, actually, this is not suitable. We have always to think about this 2 bi-phase ambiguity at C-band, and 1 phase cycle for fresh snow is also a very small amount of snow accumulation. Then VV polarization is slightly better than HH, but there is, in principle, there is no significant difference. Then the studies with C-band and L-band INSAR of Engadine confirm the findings, what we found actually in the test areas. But at C-band, we think that we need a continuous acquisition actually during the complete repeat acquisitions during the complete snow cover period. Critical issues still to be resolved. So the method from the physical point of view is very clear. We understand the physics, we understand also the processing, but there are some issues what we have to improve in the processing line and for making this working for satellite data. So what we need is reliable reference points in order to calibrate the phase to delta SWE relation. Then there is a reduced sensitivity in the forest. At C-band we are losing coherence, but at L-band we can bridge this. But at least we need to know where forests are. And something what is very important, especially also at C-band, but also at L-band, is the topography-related correction of atmospheric effects. And here we think that the EDAT product could really help. So in order to see if we can correct for this small topographic contribution what is still present in our interferograms. And that's, of course, then translated directly to the snow water current. So currently, we did not correct for this, but we hope to get some ETAT products in order to test it, in order to really go for these small phase signals. Thank you.
Yes, we are a bit over time, but since now we anyway have the discussion, we can take one question.
In the middle.
I'm not so good at this management thing.
I just have a question. It's not really relevant to the spaceborne case probably, but for your L-band airborne acquisitions, they're fairly high resolution, 0.6 meter azimuth resolution. So did you observe any defocusing of the L-band data in the azimuth direction? Or I'm just curious, like just from the absolute SWE, any defocusing effects?
Yeah, so the SWE processing was done, of course, in the multi-looking. I think it was at least 25 times 25 pixels. So we are not going with the full resolution. So we went to a resolution where we did also the measurements. So
Okay.
we are not producing the SWE map on a single look complex resolution. But the basic image had this resolution. So of course we are still in a resolution of 1 or 2 meters when we have in this direction. So
and then I have one more question. For this issue of the having a reference point, do you need a radar reference point, or can you use like a SWE reference, like a snow pillow result or something like that?
Yeah, so for the test set what we had really the corner reflectors, and we really cleaned them before the acquisition, so we were sure that there were no, and they were not just stick in the snow, they were mounted on rock, so they were really stable in the face. So they were really fixed for 1 month or more. So we drilled them into the rock, more or less. They were, of course, quite good, but at the L-band, these corner reflectors were a little bit small. So especially one or two corner reflectors had some issues. They were hard to define, actually, or to find in the images. We are looking now for a method, actually, for getting these reference points. And in high alpine terrain, sometimes this is really tricky, because if you have the face is not connected somewhere down to the valley, then of course in the high alpine regions, to find the reference point where you're sure that you have no snow accumulation or a known snow accumulation, this is hard. Even if you're using in situ measurements, they have to be representative for a larger region. And with snowdrift and everything like this in the higher alpine terrain, this can be an issue. What we think could be the way forward is a kind of combination assimilation with the snowpack model, so that you are combining the SWE measurements with the snowpack model, and if you're losing actually the reference or whatever for one place, then the snowpack model could help out for this period. So some assimilation like this would make sense. But of course, a way to find reference points would be quite good. Maybe PS could be some solution or whatever.
Okay, thanks.
Yeah, I think we probably have to move to the round table because we're already late. Sorry about that. So thanks again, Thomas, and I think you can stay anyway to co-chair the roundtable session. So yeah, and there's over here. So I think ready to join. So please stick around for the roundtable session that will start immediately as soon as we get the slides up, I think. Okay. Awesome.
You should see.
You might need extra microphones. Yeah,
We have you.
we've got one here. Yeah. Okay, right. So we have the round table that's just about to kick off, and the aim of this is for all of you, the snow and ice community, to tell us and also ESA what your requirements are. So if you need new data acquisitions tasked in certain regions that aren't covered by the current ESA missions, if you want to be able to use ESA data in conjunction with other third-party satellites, so satellites not owned and run by ESA, and also to help identify what calibration validation work we should do or what science needs to be done using all of these data sets. So we've posed collectively as chairs a set of seed questions which are now on the board. Other questions are available. This is like a starter for 10 to warm us all up. But if there's anything else out there that you think we should be asking that we haven't, please throw that out. And what we're all going to try and do is take notes of the discussion so that we can wrap it up into a summary document that will be presented on the Friday afternoon in the closing session, and also will be submitted to ESA as a written report after this conference. So, with that, raise your hands. Who wants to start? Thomas, do you want to chair? And I'll be taking notes here.
Yeah, it's good that you take notes. Thanks, Anna. So the first question is more related to science. So what are the most important science questions that should be addressed using SAR data in polar and mountain regions, but of course also the Arctic is involved. So everywhere where we have cryosphere present is meant by this, so we keep it very wide.
This only works if you talk, and we'll start picking people out and also we can all talk a lot, and so we could start picking everyone be less fun.
Anna.
Well, Thomas, I think that some of the most important science questions are, first of all, we've got this very frequent repeat period now with our SAR missions at ESA. So, Marcus will want me to stand in front of the microphone. That's what you're going to say. So I think one of the game changers in the last 5 years is the fact that we've got such frequent repeat acquisitions of SAR data. And so this will affect all of the different parameters like surface melt and snow water equivalent products, monitoring permafrost, but also in my area, looking at ice velocity and then therefore speed change and discharge change from ice sheets that we can now measure. So I think that the important science question I would say is using that dense temporal sampling of SAR data acquisitions to really understand the short-term variability in speed change and change of other related SAR parameters. That would be my answer, but open to the room. Bernd.
Those are very good points. I would argue that we are still blind, so that the dense repeat is very dense, but it's not dense enough in some areas. I think I tried to highlight that in my presentation, that it should be possible to get access to higher density data sets. This could be Explorer mission, this could be access to commercial data. The commercial sector is developing some of that to some degree. But in that, it has to be made sure that there is an agency support for that, so that this data is not accessible to only, sort of one group, but it should be more publicly available. And I think either support from a space agency or an actual purchase through a space agency and then make it available would be one aspect of that. Thank you.
I agree, Bernd. I think it is dense now, but we'll only start to sort of see more variability in that. Do you think that should be focused around sort of the SAR amplitude information, or do you think, were you mainly thinking about SAR data with interferometric capability and coherence? Or
interferometric capability. Yeah. And we also should probably identify sort of the critical areas that we would want monitored in that. On the second question, the gaps, or the third question, we have a model with the Polar Space Stars group, so how this coordination can happen. I think this should, you already mentioned 3 missions. One of them is sort of an international mission, 2 are ESA. So within ESA, coordination should be more straightforward than not, I would hope. But if you include international missions, there should be input from the science community on a regular basis in terms of a requirements document that could be a living document in a sense, and sort of updated based on new mission capabilities that come online, but also updated on findings, what we learn as a community and what we see that we still don't know in terms of where that could shape missions going forward. So I would encourage this community here to also push for a revival of the Polar Space Stars group, or a similar sort of concept to do this type of coordination. Because the model has worked in the past, I think it has worked really well. Science coordination, you know, doesn't have to be one person. Thomas and I think, showed that. So it's, I think we have a model in place that could probably easily be revived with the right political will.
So maybe one question what I have regarding this question 3 to the community here is, you know that we are getting Roselle in a couple of years, and currently it is in discussion how this will fly in formation with Sentinel-1. There are actually two extreme capabilities. So what is fixed, as far as I understood, is that Roselle and Sentinel-1 will be in the same orbit plane. But the question is now the timing. Should there be a time delay of 90 degrees, so that we have Sentinel-1 acquisition, 3 days later, Roselle, Sentinel-1 again, Roselle again, so that we are increasing the observation frequency in principle. Okay, what we are getting here is a very good coverage on one hand. On the other hand, we are losing the capability of a dual frequency SAR, which is the other option, that Sentinel-1 is flying after or before Roselle within 1 or 2 minutes, or as close as possible. So for ICE, then of course within this very short time period, we don't have big changes. We would have, in principle, of course, the L-band and C-band mission operating at the same time. The question is now for ice sheets, but also for glaciers and snow applications. What do you think is more valuable, to have a better coverage, although the frequency is different, or to have the capability of having two frequencies almost at the same time?
Well, can I have a thought on that? Because I guess one of the things that makes it quite hard to answer that question is that we don't have any in situ or airborne data sets that could help us understand how we might use the dual frequency together to get a better understanding. So maybe the recommendation, part of the recommendation could be to have a small trial in a small location.
There are a few data sets from CERCX are available, so 20 years ago, or more, 25 years ago. So where we had for 10 days at the same time L and C band. There are some airborne campaigns where this has been acquired. But of course, this is a kind of or recommendation what could be given, or we shift it to the next one when we have more experience, to support the use of dual frequency algorithms in the retrieval of snow, for example. That might be very useful, I think, to have really L-band and C-band at the same time. Just one example, we have seen here L-band is excellent for SWE retrieval, but we need to detect if the snow is melting or not. L-band is not suitable for that, but if C-band is excellently for this, so to have this at almost the same time would be an excellent combination. Also X-band would be very good for this, but this is a kind of, there are more examples for combining L and C band, what makes sense. So what do you think for your application or your algorithms or your plans, what could you actually support?
On the dual frequency side, I just want to point out, all things going well, NISAR will have a dual frequency option. It's not LNC, but it's LNS. So maybe tabling that question, if the timeline is not a big issue, to sort of, we don't have to make that decision right now. There is option.
Yeah, I think S and L band, they're quite similar in terms of, I'm not sure really if they're dual frequency model approach, as Thomas was saying, would really help. That's the question. So I think C and L band is probably better, or X band even. I would also make a plea on dual frequency estimation and not coverage, because it's so much things are changing between 3 days, specifically in snow and any kind of ice region, even though if you go for movements or velocity. So therefore, I think what we need is then closely at the same time. I would go into this direction and also include this in model-based approaches. I think that's very great. And there are quite a lot of ideas already nowadays, which
So
would...
which application do you have in mind, actually?
Yeah, SV is one, which Christina was also showing, so where you can have a help of a multi-frequency approach in order to solve this phase ambiguity. This is one part. But I could also think about other things, like more in direction of tomography, where we see different structural effects in C and L band. And if you would have both, right, depending a little bit, so you could also solve some, probably some equations here.
I mean, for modeling, I totally agree here, but for mapping of extreme events, and the extreme event can be a simple snow avalanche, like small events, you want high temporal resolution. And they really profit if you have first C, then 3 days later L band, and then 6 days, so another 3 days later, another C band.
But
So-
I think this high frequency observation is a kind of community approach from the satellite providers. So if RCM would acquire data over Europe, then we would have a very dense time series with different geometries, but still for mapping parts, also for flooding or whatever, or avalanche mapping, that could be the case. To have a L band, C band SAR is a kind of uniqueness what we have. But I think, okay.
And
Ben.
regarding the gaps.
Okay.
Two things I noticed while being in the sessions today here is something like 1 day repeat pass. Doesn't exist since ERS. So this can be a short period, a year or so, where some satellites fly very close together and then are separated further in orbit. And the question is, what happens with the end of tandem X? Do we have zero temporal baseline acquisition with Rose L, maybe, or with Harmony? Is it? Yeah.
Ben, and then Charles.
Yeah, I was just going to say that on the temporal coverage point, we probably shouldn't forget as well that we have the EW mode acquisitions in a lot of the polar areas, and if the SLCs, if those were more available, then that would help people on that front, and there would be more of a case to fly Roselle and Sentinel-1 in the sort of dual polarization version.
Okay, Charles?
One thing I've observed is just that there is often these melt events, and that the correlation at L band will recover quicker once things get cold again. So the robustness or resilience of the algorithm is sort of weighted strongly towards L band, at least in alpine areas where this is happening. If you have completely dry snow, then you might have a different preference for which algorithm or which scheduling option you pick. So at L band is definitely going to be much more robust, but still you're going to have to deal with these melt periods in between. And I don't know what that implies for the whole enterprise, just basing it on SWE. I think you also need to find a way perhaps to get snow height measurements also to help you in that process.
Hi, a slightly different view. So I'm not an ice person. I know nothing about it, but I work in the water industry sector, and one important thing that is missing when I talk to people who do water management plans of, like, is there enough water for the summer, is really having that snow water equivalent, and there aren't any reliable good products that really give the frequency of update to really let these people manage properly. And that is really that's the most important factor in all of these water management and inflow forecasting procedures. and they just use, currently I think it's mainly constants that are being used rather than actual real snow water equivalent values. So if there's anything that can be done by this community, to provide some better products for this or allow the calculation of these products, that would really be helpful for that entire industry, whether or not you're talking Europe or North America or wherever. Just a comment. Thanks.
Okay.
The products itself are neither particularly frequent nor they're quite often derived from optical data. So it's like, well, I have a giant gap there, so what am I going to do with this now? Or they're not really good over the really mountainous areas. Well, this is where the snow is. So yeah, I've not really found a good product that I've been able to advise the people to use. So just saying.
Yes, so maybe I come back to question 2. So what are the gaps of parameters, what we still work on, or what are missing for the land cryosphere? So it's ice sheets, glaciers, snow. So some of them we are working, which are not working really properly, but we are on the track. And for some others, they might be missing. Any ideas or Irina?
Yes, I think one parameter which is really missing is density, actually. So snow density, that's really a very critical parameter for a lot of different other, let me say, issues or things that you like to do, also modeling. So density, snow density is really difficult. And this is something which is only possible to get if you have long wavelengths, right, potentially, and more acquisitions, kind of a multi-static acquisition part. So this would be really great to have it. So then we could solve.
But with the current set of sensors, or with what is planned actually in the upcoming, let's say, 10 years, what is missing? For example, for snow water equivalent, so this is still not on the level of a solid, robust product to go towards the service or whatever. So we are still working on it. There in mountain terrains with 100-meter resolution. I think we are, that's my personal opinion, we are not currently in a state that we say, okay, this we can send off. So we still work on that. So other products, for example, whatever wet snow products or ice velocity or grounding line, we are in a much better position. So once we get the data on the methodological point, so I think we are quite safe. But maybe Bernd has a comment on that.
It's a simple one and probably not really simple, but DMs, time series of DMs. In terms of ever since that Tandem X doesn't seem to have a successor mission, really, that's I would think a bit concerning from my point of view.
So just to come back, so yes, multistatic means, digital elevation model, this is what I was saying before, but also that you can do tomographic acquisition. So what we need is a multistatic high-frequent acquisition. Something like Harmony, but probably with longer wavelengths would be much better. And I would agree, yeah, DEM is a good thing, but also all the rest, right, if you would have...
So L-band or P-band?
L-band would be, I think L-band is good enough.
Lucas?
I think one point which also came up during some talks is the uncertainties in ice thickness measurements, because as it stands now, I think if you look at mass changes, so the input-output method always drops off a little bit, or is like a little bit outlying compared to altimetry and gravimetry, and I think it's mainly attributed to ice thickness measurements.
So I'm not aware on the current status, but there is a kind of RINGE project, an international activity, which is actually trying to measure ice thickness from the aircraft to going around Antarctica a couple of times. But I'm not aware on the status on this yet. But that could be coming soon, but we can find that out.
Can I add into what Lucas has just said?
Can I add in to what Lucas has just said about error characterization for the
The SEC products are also error characterization for the velocity products, probably at multiple frequencies, as we have these multi-frequency SAR missions. I think it would be great to improve our uncertainty estimates so that we can have confidence in our short speed variability measurements.
I do have an add-on on the snow part in the mountainous areas where these, as Charles mentioned, also these melt freeze crusts occur, where several of these approaches that are now investigated or also work in polar areas will not work properly. So I think there may be multi-static approaches or different acquisition scenarios and techniques still need investigation for those areas.
A technique actually totally, but for this we would need a new sensors, would be SAR tomography in order to for dry snow actually, in order to estimate the snow thickness, snow height, and that is of course I think we could do some studies into this case in order to see what is possible in this case. So it's expensive and probably.
Not really a question, more a remark. You mentioned, of course, there's a lot of talk about multi-frequency. What I'm a little bit missing in this list is biomass, which, as I told earlier, let's say the name suggests it's doing only biomass, but it's, of course, I've shown this morning that the coverage actually in the Antarctic is quite well. Of course, everyone knows the temporal baselines are quite funny. You know, you've got either 3-day baselines or 9-month baseline. But still, it would be able to fill in some gaps in areas where other missions either don't have coherence or where things are really fast flowing. Within 3 days at P-band, you may be able to get something, or something that is so slow that at 9 months you still may be able to get something. We don't know. This is why it's also a secondary objective, but data will be collected. Also, don't forget that the duty cycle, the duty cycle of biomass is quite high. It's in the order of, let's say, 50%. So we're able to capture quite a lot of minutes per orbit, let's say. So this is, and the Antarctic, let's say, will be very well covered. Greenland, not at all, as you all know. So this is definitely something to work on. Then, as I also mentioned, that tomography will be something that's a phase. Of course, everyone knows that when you go to let's say, very high latitudes, then of course your baseline tend to go to zero. So it's not, but there may be, let's say, even there in the early mission phase, especially when we're doing the calibration, it may be that some of the baselines have much wider baselines, which are not interferometric at, let's say, low latitudes, but they could be able to give some interesting data, even if, let's say, on the Antarctic, let's say, periphery. So this could be very interesting, and it's, of course, it's not much data set all at once. It's about 50 kilometers worth, so it's not going to give you, let's say, the high tempo revisit that people always have in mind for these wall-to-wall mapping missions, but it may address a certain gap, and scientifically it could be interesting. And the other thing is, of course, this mission is really on the horizon. So we're talking about, let's say, in the order of 25. If we get a launcher allocated, that this thing will be up there. So it also promises something as well, I think, for the glaciological community.
Okay, thanks. Yeah, I think biomass for Antarctica is very interesting. Maybe not for the ice velocity part, because the bandwidth is quite narrow, but I think for looking or making use of this large penetration into the ice to look for aquifers or other stratigraphy in this rate, that would be a kind of opportunity. So we missed this here in the list, but of course that could be or should be studied. So biomass is coming soon, so that's hopefully, so that could be really good to study that.
So yeah, these have welcomes all the requirements for biomass that you can give us.
So what requirements do you need?
Yes, Jürgen Dahl is there.
But which requirements do you need?
Well, science requirements,
okay.
Any kind of requirements, where to have test areas, what we have to campaigns.
So this point
it's a bit late to do campaigns before launch now. But
so in order to initiate some feasibility studies and.
Some work is already ongoing, of course, because it's already for a very long time. It's a secondary objective, and actually we're planning a campaign this year in the Antarctic, and some feasibility assessment have been taken into account. But of course, we want to grow this community that is going to get involved in biomass, because this will happen always with satellite developments. They take a long time, and And a lot of this community is very mature and is used to getting thrown a lot of data at them. And if data's not there, they're simply not interested. The good thing is, as I said, now things come, so we see a lot of plasticological institutes to become, let's say, increasingly interested in the biomass mission, which we applaud to, because it is something I think we need this. Without a community, there's not going to be a use of the data. So people have to embrace this data once it starts flowing. And of course, the agency is there to help and make sure that, say, the data is going to be able to be exploited once the data is there.
Okay, thanks. Then I skip question 4, maybe, but
yeah, I had one question. It's kind of an observation that I don't see ground ice on the list for question 3. So is permafrost just intentionally not on the list because it's handled elsewhere?
It's on the list. It's So we forgot some dots actually. So
okay.
It's so we meant actually land cryosphere. So, but if you have a comment on permafrost, I think it fits perfectly in here.
Okay. Yeah. Well, my comment is the view that because there's not a lot of European permafrost, that it's more of an emphasis for RCM, or is it viewed as a goal of ESA to also be monitoring permafrost? Because if it is, then acquisitions should be optimized for that as well, I would think.
Yeah, that's a bit of the question that is question 7, actually. That was, but it's true that we could have also included in the other questions. So which kind of acquisition strategies we want and available projects. I think there are 2 things, because there are products also existing, but not enough used. Like typically we talk about EV mode before. And then there is the design of the missions for the future. And I mean, L-band will be a game changer, I believe. And I was not sure exactly about the question you asked about, like, should we have dual at the same time or shift it for 3 days? I think both would be valuable for permafrost, actually. But to start with, it's also nice to have at the same time to really study, because currently there is no operational L-band that is really usable with a good frequency. So the L-band ROSA will be a game changer, I think. But I don't know if anybody else has better comments.
My comment goes back to the biomass questions. So I had a comment regarding the expected lifetime of biomass, which I understood from the presentation is limited because of the maneuvers. And what I've noticed in many presentations now, like we make in the IC community or cryospheric community, we make use of very long-running time series. So, and there would be an option to increase the lifetime of biomass if you like stop the maneuvers at some point and just continue like acquiring. Then it takes longer to get a global coverage, but this would maybe save fuel and extend the lifetime of the mission. If I understood this correctly, is this right? Yes, instead of raising this orbit so that you are faster in having a global coverage, at the end of the mission, stopping this raising of the orbit and just just doing the rolling maneuver, and then you could extend the lifetime, having a longer time where you have a sensor in orbit to focus on processes that take long time scales to manifest themselves.
I'm not sure, Björn, if you like to respond to it. I think it probably is better if you do first. I don't know. I have a different topic.
It's interesting because we had the same discussion at Provinsar in June in Toulouse. where indeed, let's say, of course we don't know how let's say the delta V, let's say the fuel, will how fast it will go during the mission lifetime. And of course, it's clear, let's say, the mission profile is fully dictated by its primary mission objective. So this is actually how we're going to do it. And of course, maybe the length of the interferometric phase or things may change once we learn in orbit, let's say, how the data is looking like and how the retrieval goes. But then at the end, let's say, it's clear that at some point in time, the mission will run out of fuel. But it's also clear that if we, of course, at the end of the mission, it was mentioned as an option that could be, let's say, investigated at that time to see, okay, if we could just leave it floating there. But then, of course, it has a terrible, let's say, rubber coverage, but anyway, it already has basically compared to all the other, let's say, mapping missions that you could leave it there and try to extend the mission as much as you can. But at some point in time, it's clear that it will run out of fuel. So, which is a true pity, but this is what happens if you operate a spacecraft this way. Yeah.
Okay, yes, I would like to come back to permafrost because we have done some studies too on it. It's depending what you like to see in permafrost, right? The one thing is to see the slow movement, which you can do with the insert potentially, right? This is something that you do very slowly. And for these, in a moment, we do not have really sensors because we have sensors which have not timely, let me say, a good step in order to have a high resolution sensor, right, with a high frequent acquisition. We tested this with TandemX, which has 11-day repeat cycle, and we had a lot of decorrelation, so it was really difficult to get really a great coherence. So that's the first issue, so we need to have something that is timely faster if you do the insert. For the things that are very rapidly, let me say, changing, like for example, the retrographic thaw slumps, which are really fast, abrupt changes. For these, it's the best to use digital elevation models, which are high precise. More precise than TandemX in the moment is, and for these we really would think to go to higher frequencies in order to have a better estimation of the change, because if you have higher frequency you can be also better in terms of centimeters estimation and not in terms of meter estimation, so accuracies. So for, as said, the one thing is to look for frequent changes, and the other thing is really to go to DEMS, because you can't really get it very well in terms of volume change if you do only the insert, but you need a DEM here.
If depends a bit how fast, how fast is the process you're looking at? I mean, for some subsidence in some areas, you can have centimeter to decimeter within a season, which is then possible to measure quite well with multi-tuple INSAR, S-pass, for example, or but X-band is not ideal, indeed. Then you lose currents pretty fast. But C-band has shown that it's possible, and L-band will probably be even better. I mean, there is data, ALOS data, SAOCOM data for testing L-band today already, but Rosal, I think, will be a game changer for that. Yeah.
Yeah, we are not only looking on the insert, so deformation, which means really change, but we are looking for volume. If you like to see how much volume on material is deposited, then it's good to have it in.
Yeah, you can infer, that's true. And I think the main point with maybe the question 5, because a lot of the INSAR-based permafrost studies are actually inferring active layer thickness, inferring ground ice content, inferring, but there is a model behind, and there is not a lot of ground truthing. So that's probably the big gap is the validation part. So supersites and of course in these regions you have a funding issue for that. So maybe that could be a recommendation to have actually funding possibilities through space agencies to really have a good CalVal campaign for permafrost.
Okay, then we are at question 5, I think.
Thomas, can I just jump in? Sorry, you can't see me because I'm sat on the floor. I'm trying to charge my computer, and I need to take notes, so that's why I'm down here. Whilst on the topic of DINSAR, stupid question. Obviously, when we get C back up, we're not going to still have coherence on Pine Island and Thwaites. Bernd, are you expecting interferometric coherence from NISAR over the Amundsen Sea glaciers? You had it as on your conclusion slide, but I just want to make sure whether that is a gap or not.
So based on some pulsar results, we can track the main trunk of Thwaites, but on phase, I don't think the 14 days were not successful for phase analysis, and so I think we're going to miss the grounding line even with NISAR.
Sometimes.
Sometimes, yeah.
Yeah.
So we don't have a continuous observation system. And I just wanted to make one point while I have the mic. All of these, cutting edge and new aspects are considering that ESA is committed to maintaining sort of the current Sentinel-1, or if there is 2 Sentinels again, to have this 6-day repeat that we had in the past. So we assume this is the baseline, and this discussion is for new and improved acquisitions.
Yes,
is that correct?
What I know from Nuno, that this is the plan actually
Okay.
to implement
Perfect.
this. But
Thank you.
okay, that's with a question mark, so this is not confirmed yet. Yeah, but we can actually put this in the recommendations to implement for Sentinel-1 AC, for this combination, a kind of continuous observations of the margins with 6 days in Antarctica, and continue the observations of Greenland and the other ice caps as it was with 1A and B, to have this actually maintained.
Yes, I wanted to stress 2 points that Lynn was already mentioning before. One is about the acquisition strategies. So, of course, the most obvious gap now we have for permafrost is about Siberia. After the failure of Sentinel-1B, we don't have any acquisitions there. There's nothing we can do. Still, taking into consideration now the political situations that cannot cooperate with the Russian institutes anymore, that's a pity. So I think for the permafrost community, if there is a priority to set on the production of the EWSLC, that will be the coast of Siberia. And then the second point I wanted to make is on calibration validation campaigns. So there are some, or maybe even a lot of in situ measurements for subsidence on permafrost areas. They're done by the permafrost community, but now we also have some remote sensing products. So we come up with these products, and then you see sometimes discrepancy. You ask them why you didn't measure there. Where we see most of the differences is that because we had different objectives in mind. And now with these remote sensing products, we can also better planify some calibration or validation activities that I think from the remote sensing from the space community, it can be, given some ideas and way to do it.
So that's a kind of coordination between the permafrost community, so in situ people, and the remote sensing one. Okay.
And that's something we can do now because we start to have the remote sensing products.
That's an excellent idea. Are there any other needs for campaigns, Calval campaigns, for new products or?
Yeah,
okay.
well, just a short addition to this, what you were commenting, Thomas, about this acquisition plan for Sentinel-1 and Rosel. It is worth it that they go side by side. And I was just wanted to say that in Sodankula, in Finland, we have this Muron-based radar that has this L-band, S-band, and C-band and X-band. And I was just wondering, and this is a question if this data set can be used somehow to push and leverage this decision.
That's excellent.
Yes, I forgot to mention that this has been used in the past for demonstrate sea retrieval.
Other campaigns needed for ice sheets parameters?
We need to have the stuff on ice sheets and ice shelves.
And ice shelves, yes, okay.
For campaigns in Calva, a question. We have been using, or we have been digging in and digging out a lot of corner reflectors in snow. And are there any studies or experiments using active transponders as phase reference? Might be worth to consider. I don't know if there are any experiments with that.
Yeah, Then of course you are related towards infrastructure. You need power and so on. You can put them somewhere in remote areas, especially, okay, within the Alps or Norway or whatever. So this is probably quite straightforward to
That's
do.
obvious disadvantage that you need power, but you could put a solar cell. But is it more complicated putting there a solar cell or digging out the corner reflector for every pass of the satellite?
I guess in this regard, in this super site in Sodankula, we have the infrastructure. So it's just, if you want to test this, it's just a matter of taking this transformer there and setting them.
Cheers. On Calval and for error estimations, uncertainties, I think there is, from my perspective, there's scope to do much better on errors in ice speed measurements. I think that the community doesn't necessarily have a unified, agreed kind of method for that, for calculating those errors when we do velocity tracking, and I think we could do a better job, particularly if we're looking at short-term speed variability in Greenland and Antarctica and the impact that has on mass balance. I think that there's definitely gains to be made by doing that, and a Calval campaign is one of the ways of nailing that down. I think there's a good argument to do it, perhaps in difficult to track areas like in Antarctica or Greenland. Oh, yeah. Yeah, there's particularly where there's surface melting and changes in scattering horizon during the tracking results. I think that's an area that's poorly constrained as well. Okay. Yeah, definitely. Thanks, Anna.
Okay, so we have 2 minutes to go still.
Yeah.
So if you have any urgent question, you can, to any of these questions what we have here on the board, that's now your chance. Yeah, fracture. But if you have any ideas overnight or whatever, just send this to us and we will include it in the recommendations. So I think you have our email numbers until, I think, Thursday evening to include it in the recommendations so that it will show up finally in the recommendations to ESA and will be also presented actually on Friday afternoon. We will, as a team, we will collect all this information and write it up and present it on Friday afternoon, I think. Then I think I want to thank all the speakers in both of the sessions, in the morning and in the afternoon. I think it was very fruitful for us, and I hope you also enjoyed it, and I hope to get some more feedback on these seed questions here in the next hours or 1 day, 2 days. And I want to close the session here. Thank you.